Alright. Oh, I hit this stop suddenly. Uh, 1.5 rounds. We will get back to the paper, first paper, position bias, and learning to rank, and whatever it is. Yes, by the way, I wanna talk nice. I wanna talk like I'm talking to you. That's enough. Enough is enough. I don't like it we will start with pool. What's wrong? It's a slick. Oh shit, man. Jeez. Why did you become so fast? Oh. Never thought I would kill. Ah, fuck. That's actually fun. I should have turned my... Okay, chill the fuck down. Jesus. Oof, this guy is good. Wait, who killed me? In his neck. Second time's a slick. Jeez, they are so good, alright. It could be my third time actually. Damn, this guy fucked me over. How many times do you wanna kill me? Machine gun is the best in the pool. It's a close distance. Jeez, that gun. Oh, so sleep is the number one. Dude, actually I did really good. Oh, why? Why everybody is so I'm down, guys. I'm down. I'm a down guy. Felt good. Felt challenging. I thought my record would be much worse, but much worse. I want to speak slower this time. Slower, louder, and deeper voice. So, I want to talk like a retarded. That's, oh shit, dude. Again, sleek. Oh, it's actually a cat. Oh, in his heart, Jesus. Oof, baby. Ah, Jay, why didn't I change my gun, by the way? That's... Ah, bitch. Ah, bitch. Ah, bitch. Onion. You know. What's up? I'm here to kill you all. Oh shit. Oh. Jesus. I killed him. How did he kill me? Bruh! Fuck you. Bruh! Come on! You fucking assholes! Stop this shit. Ah, I finally killed him. And I finally killed you. Motherfucker. Oof. That's called focus. That's not... That's saying no to distraction. Jesus, boy, who's that? Pedro. Where are you, loser? Do you see power from close distance? Dude, it was mine. Shit. I was lucky actually. Jesus. Bro, I just didn't even see anybody. Wow. Somebody else killed him? That's funny. Oh shit. Damn, dude, I'm just dying. Finally, bro. That was annoying, to be honest. Disrespectful. Low on ammo. Dude, so many bullets. I'm just dying. Dude, I was number 4 and now I'm... Jeez. Yeah, shoot whatever you want. I'm not gonna... That was called teamwork, motherfuckers. Got out of my sight, otherwise I would kill him. This is a close distance. Oh, come on. This guy's This motherfucker is dumb. Bro, what was that? I was dead by definition, and this guy... And this guy was killing me good so far. Oh, bitch. Oh, shit. Ah, shit. Every side. This is a crazy game, guys. You go off. No! That was the... Oh my god! Terrible! Fuck, dude, that sucks. Why should I get knifed? Jeez. That was cold. I used to feel more comfortable in the shoots. Now I'm feeling more comfortable actually in the baggage. Where are these fuckers? Jesus. I felt it in my liver. Thank you. escape all the time. Ooh, I got him. Yeah, when they have a sniper, I should not stop. Stand. Ooh, motherfucker. What an arrogant person. Jesus. Well, this part is covered. I will go the other side. It seems we got them all, so I just jump. There's nobody. Oh shit, who? I didn't see where he killed me. And then we're gonna. Dude! Who's. Again? Ah! I think we had a setback. Not actually the whole team. Jeez, don't kill me here. That's bullshit. Same person. Ah. Jeez, he has a bad gun. Bitch. Can't stand it, bro. Straight right there. Dude, how many should I shoot? Who killed? Oh fuck. Alright, motherfucker, come over so I kill you. Dude, I knew he was there. Still he killed me. He has nice movement. Oof, I have my favorite gun. Dude, with this gun, I'm just... Shoot me, I will come back at you. This motherfucker is trained bad. He thinks he can come to our isle every time. Fuck off, dude. It was his second or third time, actually. Who? Where was it? One shot, so easy. Oh, he has a snipe, motherfucker. I'm actually behind all this motherfucker. I'm even in the lead. Oh. Woohoo! That was so fun. Who shoot you? bad, bad issue. That was what we deserved. Oh shit, these motherfuckers are so... This guy really, really killed me. Like how? Wait, who taught you? Ooh, where are you? Where? Jeez, okay. Stay back and just watch them. Alright, that's the rule. Come here if you want to kill us. Switching my mode. Oh shit. Let's be honest, I'm doing a bad job. Fuck. That was terrible. Fuck it, I have to exit. Fuck it. First round was the best round. That's... Okay, paper.
On users clicks 20. A prerequisite of fully leveraging the power of click data is to debiase it.
Debias.
As a result, their click data in personal search provides implicit but abundant user feedback. It thus becomes a natural source to improve personal search quality. However, a well-known challenge in learning from click data is its inherent bias, position bias 19, presentation bias 32, and trust bias 26, etc. Among them, the position bias has a strong influence on users' clicks 20. A prerequisite of fully leveraging the power of click data is to debiase it. As a result, there has been a great deal of research on extracting reliable signals from click data. One such effort is known as click modeling. Click models were initially proposed for web search with the goal of estimating query, document relevance by taking the click bias into account. 9. The position bias model 27 and the cascade model 10 are the two classic click models. In the position bias model, users' clicks are determined by two...
Actually. The position bias model and the cascade model. We talked about it previously. Known as click modeling, click models were initially proposed for web search with the goal of estimating query document relevance by taking the click bias into account. The position bias model and the cascade model That's what we needed actually are the two classic click models in the position bias model. User clicks are determined by, and I'm happy that we have these models. We don't need to find the answer for these solutions. For this, we don't need to find the answer for this solution because they are not a problem anymore. The cascade model assumes sequential user behavior. A user scans documents one by one from the top, and the scan continues after a non-relevant document but stops after a relevant document. More sophisticated models are these built upon these two classic models. In the learning to rank settings,
Factors. In the learning to rank setting, the existing click models belong to the pointwise category because they estimate query, document relevance but not based on the correct order of documents as in pairwise and listwise approaches. Different from click models, Joachim's ETAL19 studied a few heuristics in the pairwise manner, example skip above, and found that these heuristics lead to more reliable relevance assessments. However, the data obtained by these heuristics are systematically biased and a ranking function learned from it tends to reverse the existing order 20.
what is happening? 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 What is happening?
Here's the passage repeated as requested. Recently, Wang ETAL31 and Joachim's ETAL20 introduced the unbiased learning to rank framework by treating the bias as a counterfactual effect. Inside the framework, the critical component is to quantify the click bias, rather than estimate the query, document relevance in click models. Due to this difference, randomizing results on a small fraction of search traffic is sufficient. In this paper, we study different ways of position bias estimation for unbiased learning to rank.
Oh, different.
Result randomization intuitively degrades the user's search experience. We quantify the negative impacts of different degrees of randomization, RAND top N and RAND pair, and compare their effectiveness for bias estimation. This naturally motivates us to study how to estimate the bias from regular clicks. The classical position bias model is a candidate method. A direct application of this model requires the same query, document pairs appearing at multiple positions multiple times 7, but this is not realistic in personal search. We propose a novel regression-based M algorithm that does not need the query and document identifiers but works in a feature space. Such an approach is applicable to any ranking system where clicks and ranking features are collected. It also greatly reduces the pre-processing that is usually needed in standard click models. Furthermore, as position bias can potentially change as a ranking system evolves, our approach can be used to re-estimate position bias without any intervention like result randomization. The contribution of this paper is summarized as follows.
As Furthermore, as position bias can potentially change, position bias can potentially change. Yes, we want to say in a bigger picture, position bias also depends on the items in the ranking. Where is it? As position bias can potentially change as a ranking system evolves, our approach can be used to re-estimate position bias. That's what I like. Sticking to 1 over log 1 plus pi, that is just a starting point. We need to update without any intervention like result randomization. The contribution of this paper is summarized as follows. Let's go. So far, everybody is confirming.
We study the problem of position bias estimation and result randomization and propose a regression-based M11 in personal search that can be applied to any ranking system without the need for intervention. We compare different degrees of result randomization based on effectiveness of bias estimation and negative impacts on an email and a file storage personal search service. We conduct extensive experiments and our results show that position bias estimated using AM can achieve surprisingly good results without using randomization, and that pairwise learning to rank algorithms can better leverage these bias estimates than pointwise ones. The rest of this paper is organized as follows. In section 2, we review previous related work. The unbiased learning to rank is set up in section 3 and is followed by different methods of propensity estimation based on the position bias model in section 4. We present our extensive experimental study and our evaluation methodology in section 5. Finally, we conclude and discuss future work in section 6.
Alright, the related work section, I'm not a big fan of, but we will do it. By the way, just let's skim through it and get the juice of it. Don't, this is fantastic, this is what I want. I read so many fucking papers in my life. None of them are fantastic, dude. Bullshit. Just read them so that you can say, oh, okay, I gave. At best, a paper can give you an idea. That's it. Fuck them. Paper should be just the story of what we did as our project. That's it.
Here's the passage repeated as click-through data has become an indispensable resource in both web search and personal search. There is an abundance of prior work on click modeling in web search that addresses click bias to extract useful signals from click data. One of the seminal papers by Joaquims et al. 19 evaluates a few heuristics via a user study and shows that clicks are valuable as long as certain biases, especially the position bias, are accounted for. Many click models have been proposed to model user click behaviors based on probabilistic graphical models 7 to 10, 14, 17, 27, 34.
That's just good to know that
these models can account
exist,
for the click bias
and
and
if
provide
you want,
more
you
reliable
can
relevance
use it.
estimation between queries and documents. Unbiased learning to rank takes a different approach to account for click bias. Wang et al. 31 study the selection bias at the query level when click-based training data is collected in learning to rank. Joaquims et al. 20 present a counterfactual inference framework with a principled theoretical basis. Both approaches rely on inverse propensity weighting, IPW, developed in the causal inference field 28, and both rely on result randomization to estimate the propensity. Our paper is in the same unbiased learning to rank framework, however, we estimate the propensity without randomization. Our work is related to recent work on personal search 2, 3, 6, 22, 33 that emphasized relevance-based over time-based ranking 6.
What is time-based ranking?
User behaviors in personal search show different traits compared with web search 2. For example, repeated visits to the same results are less common in email search. Thus, applying learning to rank techniques is important. However, the click data is highly sparse in personal search. We use a regression-based M algorithm that extends the standard M algorithm to handle the highly sparse data effectively. Inverse propensity weighting is a commonly used technique to address sample bias. It has been adopted for unbiased evaluation and learning, example 1, 12, 23, 24, 29, 30. Most work in this area assumes that the propensity scores are present in the logs and study how to reduce model variance while staying unbiased. The unbiased learning to rank framework is different in that the propensity is not explicitly logged but buried in the user behavior data implicitly. How to estimate this propensity in a less costly manner is critical in unbiased learning to rank and the focus of this paper. Here's the passage repeated as requested. For simplicity, we assume that a click document is relevant. Note that such an assumption can be relaxed to accommodate noisy clicks in unbiased learning to rank as shown in 20. However, the reverse is not true due to position bias.
For simplicity, which, don't forget that the RIBPI system is for a homogeneous list, there is no mismatch between intent and query, so this is good actually. For simplicity, we assume that a click document is relevant. What do you mean? What are the other options? Note that such an assumption can be relaxed to accommodate noisy clicks in unbiased learning to rank. Fuck. As shown in 20, however, the reverse is not true. If something is relevant, that's not necessarily is got clicked on. To position bias. Relevant documents may not get clicked all the time because users do not always scroll down the list to examine them. That's true. Thus, click data obtained from search logs is biased due to unobserved feedback. That's the flooding and everything. Learning from it without accounting for this bias leads to less effective ranking functions. In this section, we review and discuss different ways of unbiased learning to rank. Let's see what it says. Can you close? In the learning to rank setting, there are two existing propensity-based bias correction methods. In the following, we use a Bernoulli variable O, which says it's observed or not, to denote whether the relevance of a document is observed. The variable O can depend on various factors such as position or even an entire rank list. Without loss of generality for ith document, we use a weight notation OI equal 1 to denote the propensity that, why don't they say probability? OI is 0, 1 to denote the specific value. We use RI in 0 and 1 to denote whether a document is relevant, and use pi to denote the list of ranks of end results. Perfect. Everything is matching. Query level propensity. That's a good notion. A key observation in 31 is that query without clicks are not useful. Queries without clicks are not useful. think everybody should watch Sam's last video. That was very interesting. That he said, as a CEO, he made the best team, and it is the most important task of a CEO. But the team got so good and efficient that they didn't need him anymore. So he has to leave. Query level propensity. A key observation in 31 is that queries without clicks are not useful in the pairwise or listwise learning to rank approaches and not included in the training data. Hence, due to the position bias, queries whose relevant documents are ranked lower, well, that's related to what Ehsan was talking about, blind spots. Queries whose relevant documents are ranked lower can be underrepresented in the training data. The propensity that the query is selected in. Probability of being observed for query queue, item I being observed for query queue. Oh, okay. Where IQ is minimum of i's in pi where the relevance is 1. What do you mean I in pi? Pi is not a set, pi is a permutation. But okay, it's talking about the first one, huh? The bias is corrected by using a query level inverse propensity weighting. Why that? 1 over problem. Highest position of its relevant documents. What is pi again? Oh, Ri is also 0 or 1. Oh, I thought it's in the interval. So either, well, this is a very simplifying case. Either they are related, relevant, or not. I love simplicity and simplification. To denote whether a document is relevant and use pi. Okay, pi is just this list. It's not a permutation. All right. First item, first document that is relevant. Such an approach fits perfectly well when there is a single click per query, but can be less accurate for queries with multiple relevant documents. Document level propensity. That's actually really interesting. Document level propensity. Document level propensity is this document level. What was the other one? Query level. Query is related to the whole list, but document is each item. Document level propensity is studied in 20. It starts with a performance metric that measures the rank of the relevant documents. What does that mean? As rank. Rank is sigma RII. RI is the relevance, right? So if it is relevant and we want to minimize the rank. In bias data, IPW is to use to correct the bias, rank hat, not hat, what is it? Underline, overline. Sigma over all of the items that they are observed times the relevance over this, which is I, because I is either 0 or 1, and over PO of I being observed. The rank metric is proven unbiased. Wow, what do you mean the rank metric is proven unbiased? Expected of rank hat over rank bar equals rank. The document level IPW is this. Alright, I don't know what proven unbiased mean. Let's check it actually. Unbiased learning algorithms. The rank metric can be optimized by a pairwise learning to rank method, such as SVM rank. To show this, let Si and Sj be the scores of a ranking function. For document I and ij, rank can be expressed as a pairwise loss using the indicator function. So all of them who are observed and are relevant, sigma their wi, which is their propensity, times their I, and plus 1 wi times the same, is I equal to okay, all of the items who are after or below item I and have a greater score. This doesn't end up in I. How many items? Mm-hmm. If first of all, we don't know if Sj is bigger than Si. We sort them based on their S. Is it an assumption? Then that would be I, yes, because it will be J minus 1. I get that. Let's see what they say actually here. Expected value of the IPW corrected rank metric equals the true rank metric. Sum of the position of the relevant documents, and we want to keep it as low as possible, right? Mm-hmm. That's actually something we did too, right? Look at this one. So here we're saying the number of the users clicked on products from type 1 over n, and you may say, okay, I want to add this probability of being observed. So we also match this. I get it, but why not? Why just over it? Why not over it squared or something else? Because it makes it unbiased. That's nice. Note that we can extend the sum over all I because OI is 0 on observed positions and thus 0 move expectation inside Ri is constant. They don't depend on OI. Exactly. Okay, OI depends. That's the thing. Yeah, I is constant. Alright. I is constant. Exactly. Yeah, if you are going for a general, in general, yeah, you say that the probability of being observed depends on our eyes. However, if we are designing something that is, we are not observing their RIs, we are designing an algorithm that works for every query, for a general query, we should assume that this probability, if it exists, does not depend on RI. Then we may, for next steps, you say, okay, they may also depend. Definitely depends. If you look at the list, if you look at the text and it is nice to you, just you enjoy reading it, you keep reading it. The same with the list. If you the same with the list is different. No, it's not the same with it, because for a list, you may say, if it's a list, really good list, at the beginning of it, I find what I want and I leave. Right? That's the point of a list. Is not the point of a text. The point of a text is probably, if it's interesting, make you leave and make you keep reading. Point of a list is just you want to find what you want right away and ends up in purchase. The loss above is upper bounded by the common classification loss function, the things loss or the long loss, and can be optimized. Sorry, I use the speechify too much. The loss above is upper. Okay, what is the loss above? That is the loss above. The loss above is upper bounded by the common classification loss function, the hinge loss or the log loss, and can be optimized by pairwise learning to rank algorithms by constructing the following preference pairs for each observed and relevant document I. We pair it with each of the other documents J in the given query and create a preference pair I greater than J. Note that the weight for each pair is only determined by WI, the IPW of the document I, given a single click training data. Both query level propensity and document level propensity lead to the same pairwise learning algorithm. For multi-click training data, the query level propensity can be adapted by replicating a multi-click query to multiple single-click queries with each corresponding to a click. It is click, click, click. It is easy to show that such a strategy of the query level IPW leads to the same pairwise learning algorithm as document level IPW. In addition, both rank and rankr can be optimized using the lambda gradient in lambda loss and lambda mort similar to rank. We can define the DCG-like metric prec and its IPW version prec bar as follows: Ri over I. What is prec? Precision? Precision 1 over I, and prec bar Wi over I. What is prec? Oh, that's like DCG like. Prec is also provenly unbiased. Expected of prec bar is prec. We use prec in our paper as the optimization metric, and other types of DCG like metrics can be used easily in the current setting. In the unbiased learning to rank framework, the critical part is to estimate the propensity. Note that a nice property of the current metric is that we only need the propensity of observed and relevant documents, y equals 1 and ri equal 1, and we do not need the propensity of non-relevant documents. Such a nice property holds for pairwise learning algorithm because they closely related to meta-analysis in which non-relevant documents have no contribution to the metric values. However, it does not hold for pointwise learning algorithms because a non-relevant document usually contributes to the pointwise loss function. We will show some attempts in our experiments, however, how to extend the IPW method to pointwise approaches is an open area of research. By the way, I remember that we said the model that users do not know their intent and they are finding it, but they know Q. They know Q about it. They know it is Q. What do I want to say about it? So this case, their type is actually not V1, V2, but the set V1, V2, something like that. Or Q. Q is V1, V2 actually. Yeah, I don't think it's a big thing. Okay. Propensity estimation. Oh, that's nice. Probability of observed. Probability of click. Go and query, document, and K, what is the rank? Is probability of being relevant given the query and the document times probability of E, what is this? E examined given the rank. That is the middle part here is the one that says what's up. Okay, it's 3:30. So what we have is the probability of click. What we want to find out is the probability of examination and probability of relevance, or in other words, how relevant it is and what is the boost effect, right? But these are again very computer sciencey. They are not economic point of view. They don't give us how a user selects. Well, okay, they say, okay, if it is relevant and we observe it, but it doesn't say what is user maximizing. I see, in a sense it gives us, so okay, not very terrible. The position bias model assumes that the observed click Bernoulli variable C depends on two other hidden Bernoulli variables E and R, where E represents the event whether a user examines a document. What is the difference between examination and observation? Why they use the new term? I don't know. Represent the event whether it examines a document at a certain position K, and R represents the event whether a document D is relevant to a query Q. We had this discussion where probability of C equal 1 is the probability of clicking document D that is shown at position K given query Q. Probability of E equal 1 given K is the probability that was examined. The model assumes that the examination only depends on the position. That's a big assumption, but I like to have it in my model too. And the relevance only depends on the query and document. We use the following shorthand of derivation. But to be honest, I don't think observation is only a function of position. It also depends on relevance. If all the top 5 items are not relevant, you will end up, and you have a sequential behavior, you will end up seeing the 6th item, no doubt, right? And 6 is not very low in the list, so obviously this is a not true assumption, but it's a good assumption. Because we are assuming sequential behavior. Yeah. But in general, I agree. It depends on the list itself and the relevance. But it's too much for us if we think like that. Theta k is probability of observation, and gamma qd is the relevance, probability of relevance being 1 actually. Though simple, this model has been shown to be as effective as a more sophisticated click models. That's the beauty of it. You can assume simple models and they still work. They have untrue assumptions, but they are simplifying assumptions. And these are good assumptions and they work. In particular, when there is a single click per query, this model is equivalent to the user browsing model that achieves the state-of-the-art performance. On the other hand, more sophisticated clique models can be potentially used as well for propensity estimation. So that's a simple model that works very good. Why don't we use it? I want to use it. In the position bias model, the observed variable O is equivalent to the examination. Of course, that was what I was talking about. That was what I was talking about all the time. This has been proven in 20. I don't know what you are proving, but they sound similar. When E is 1, the relevance R is fully observed by C and thus O is 1. When E is 0, C is 0, always holds, and document may or may not be relevant. In another word, we have no knowledge of R and O0. Actually, what I'm understanding, I like these approaches better, these models better. Fuck your utility function. Fuck maximizing utility. Economics stupidity. With theorem 4 because they're simpler. With theorem 4.1, and they work. They're simpler and they work. That's it. Estimating propensity. Economics model do not work. They do not let us check them. Fuck you. Equals to estimating the examination probability P of E equals 1. Also, a clique document I means it is examined and relevant. In other words, it is relevant and observed, and thus we only need to estimate and apply the propensities. Dude, you can assume simple user behavior models. I think these models, these simpler models, work really good when we are looking at the real data and we want to come up with some numbers, but they are not good when we want to theorize, and say, okay, let's assume a rational player, and this takes this behavior based on this model. What will be his choice? They don't work there well. They work nice when we look at the data, real data, in real world, and say, okay, what are these probabilities? Because we can take average with the data, and all of these will get a number. But if I say, okay, I have a ranking, and user just picks the item that is relevant, and once he observes it, and if it is relevant, they pick it, then all of our rankings strategies do not matter, because they just look at the first item and pick it. Yeah, let me write it down. Like counterfactual. User behavior models. Probability of C equals probability of R times probability of observation are good once we look at the data and want to find these probabilities. But they are not good to predict a user behavior. Does it make sense in theory? Actually, I think I bullshitted here. I think I said bullshit. But let's have it here. Let's have it here. I don't want to clean it, but erase it, but let's have it. So examination and observation are different. Alright guys, I have to go to my group meeting.